Okay, we're going to beat this horse to death. It just won't die. I've corrected the labeling over here. This top trace is pin 3 of the 555, and that's the 0 line. And this bottom trace is the drain of the MOSFET, and that's its 0 line. And you can see the parasitic oscillations, or the oscillations that are happening right there from the 555 timer, and then those are the parasitic oscillations that are being induced by the MOSFET trying to turn on a little bit prematurely under the influence of those guys right there. Now what I've done is I've taken off the big variable pots, and I've replaced them with small 10-turn trim pots on the board here, which gives me a little bit more precise control. And so what I have found is that if I take and vary that duty cycle trim pot, you want it there. Now watch those tiny little parasitic, those little oscillations. If I vary this pot, especially if I turn it in the right direction, there, I get to the point where, that I was showing before, at some point. Sorry this is taking so long. I have my hands full, literally. It's a little bit more difficult to adjust that pot. Okay, there you go. So as I get that, as that oscillation goes shorter and shorter and shorter, it reaches a point where it goes boom. The scope loses its trigger, or does it? What's really happening, I've determined now, is that the 555 timer is actually feeding back itself, and if you change the time base, you can actually resolve that high frequency oscillation there that's coming from the 555, and that the MOSFET is trying to reproduce before it turns fully on. So, okay, so we have a number of things happening. The scope is losing its trigger sometimes, but sometimes it's also just a matter of the frequency of the oscillation changing so much. So here I'm going to go back to the duty cycle and tweak it so that it comes off that oscillation point, and now that's, of course, we've changed the time base, so you don't see anything except a straight line there. But there's that feedback oscillation at certain duty cycle. There you go. There's that. Okay. And let's see, what would the frequency of that be? We're on 1 microsecond per division, and we have yeah, we're on 1. Let's do it at a 1/10 of a microsecond. 1/10 of a microsecond per division. That's why I have a frequency counter. It's really hard for me to do this, but at 1 microsecond per division, we have 1.5 complete cycles, it looks like. Or in so that's if it's 1.5 complete cycles, that's about 1.5 megahertz at 1 microsecond per division. So that's the frequency of that oscillation. It's pretty high. Anyway, so we have a feedback oscillation. It's not a parasitic oscillation in the 555, but it is inducing this oscillation in the MOSFET. It's a completely regular oscillation. Even if when the time base is So when the MOSFET shifts into that higher frequency mode, driven by the that feedback from the 555, and it's like shifting frequencies, right? So it's no wonder that energy comes through the MOSFET when that happens. The MOSFET is actually staying on a little bit all the time. There's no duty cycle, and the thing can actually, it is resolvable. And thanks to Aaron for making me test my hypotheses, I've actually added a little bit to knowledge by being wrong and proving myself wrong, and at the same time proving Aaron wrong. So we're not seeing a random chaotic oscillation in there. We're seeing the MOSFET amplifying a 1.5 megahertz feedback signal coming from the 555 timer. Right.